Hello, students. So we are going to take a quick break to introduce a new thing, a new definition. And man, does this have like a really unfriendly name to a student approaching it for the first time. These things are called Stirling numbers of the second kind. And you're like probably already thinking, oh man, I don't even remember learning Stirling numbers of the first kind. And it sounds a little like, the title to a Steven Spielberg movie, Close Encounters of the Third Kind, and it's got 1, 2, 3, 4, 5, 6 different words in it. It's not like Fibonacci number, or something like that. But for now, this is the only type of Stirling number we're actually going to be talking about. So you could just think of this is our only Stirling for right now. It's only in certain situations, which we'll get to, where we might have to consider the other type of Stirling number. Okay, and the notation, well, instead of CNK or PNK, we're going to use SNK. And this is going to be equal to the number of ways that we can split n distinguishable objects into k non-empty subsets. And these are not distinguishable subsets. They're just into k subsets, not subset 1, subset 2. These are k, let's say, indistinguishable. Now, of course, if we have a set, if we're thinking about the normal mathematical definition of set, we don't have repetition in a set. Each thing only appears once. So if you have the set 1, 2, 4, 4, 1, 1, 2, it's the same as the set 1, 2, and 4. And the things in the set are the distinguishable things. If we couldn't distinguish them, they would collapse upon each other. So I could have shortened this by saying, hey, it's the number of ways we can split a set into a set of size n into k non-empty subsets. And it doesn't really matter what's in the set either. So I could have even said it's the number of ways we could split the numbers 1 through n into k non-empty subsets. Number of ways I'll leave the indistinguishable here though. Non-empty subsets. Okay, and now let's start off with some examples. So let's start off with maybe 3. Okay, and this is another notation as well, but you know what? Let's just jump into this right away. So let's try to do S3, 1. Okay, so S3, 1, how many ways can I split this up into one non-empty subset? Well, I have to put everything into that subset, and I'm done. Let's do S3, 2. Okay, how many ways can I split these 3 distinguishable elements up into two non-empty subsets? Now, it doesn't matter which one's on the left or which one's on the right, because this and this count the same, right? Because the subsets themselves aren't distinguishable from each other. I could maybe even make, doesn't really help, but I'll make a little blob here, right? But this is not subset 1 and subset 2. They're not labeled. So this counts the same as this. I just want to know the number of ways I can split them into subsets. So what I could do is I could do red by itself, because they have to be non-empty. So one's going to have to get 1 and one's going to have to get 2. So I could do red by itself. I could do oranges by itself. Or I could do yellow is by itself. Oh, well, there's 3 possibilities there. Those are the only ones. One has to have 2, one has to have 1. They are non-empty. Okay, now let's look at S3, 3. Okay, so now I have 3 subsets. Oh, 1, 1. I'll make a little circle for yellow so it doesn't feel left out. And 1. Red, yellow, and orange each get their 1. And it doesn't matter what order they are because these are indistinguishable subsets. So those are some Stirling numbers. There's only one way to do that. Okay, let's maybe take it up 1 degree. Let's toss in a green. That looks kind of dark, but that's okay. Toss in a dark. It's kind of forest green, it looks like. Okay, so I want to find S4, 1. Okay, this is how many ways I can put 4 into one subset. Oh, they all have to go into the subset. Well, they all have to go into the subset. Okay, now let's do S4, 2. Okay, so now we have to be a little bit more careful. Let's think about this. Okay, now I could either do, there's only 2 subsets, so this is not here. And I could either do a 2-2 split or a 1-3 split, but that's it. I can't do a 0-4 split. Okay, so I could think about this as red has to get paired up with something. If red gets paired up with yellow, then these 2 are together. If red gets paired up with green, then those 2 are together. And if red gets paired up with orange, then those 2 are together. So that's 3 possibilities for the 2-2 split because red must get paired with something. Okay, now let's try the 3-1 split. Okay, so we had 3 so far. Okay, well the 3-1 split's easy. Either green's by itself, yellow's by itself, orange is by itself, or red is by itself. So 4 possibilities for the 3-1 split. So I get 3 plus 4. I'll just leave it like that. You can do that one. You can finish that problem on your own. Okay, S4, 3. Okay, so now I have 3 subsets. Okay, now they must be non-empty. So that means I can't have any. I have to have something like this. I have to have 2, 1, and 1. Okay, so let's think about this. Well, I could choose any 2 of the 4 to be together because it doesn't matter where I put them. This is the same as this is the same as this. They all count the same. They only count once for this and this and this. That only counts once. So as long as I know which 2 are together, I'll be good. Okay, so how do I know? What are the possibilities for having 2 together? Well, I have 4 objects. I want to choose 2 of them. 4 choose 2 is 6. And now finally, S4, 4 is going to be 1 because 1, 1, 1, and 1, and it doesn't matter what the order is. So those are some examples of Stirling numbers of the second kind. This is the type of Stirling number we're looking into. We use this capital S and K for these Stirling numbers. Different books use different notations. There's a lot of them. This is a nice one. Also, this one is also commonly in use for this. But many of them will have like a little number 2 or a Roman numeral 2 or something else like that. It might be a choice for uppercase or lowercase or different things. So do pay attention to whatever book you're reading at the time. And this is none of the real theory, but just the very definition of what the Stirling numbers of the second kind actually are. And we will need that moving forward.